let us move on to our next talk. Jakob Moritz will tell us about KKLT and resolutions of it.
Thanks very much. I'm excited to talk in our first session in 2021. And I'll tell you about resolving spacetime singularities in flux compactifications and KKLT. And this is based on this recent paper with Federico Carta. And it's at various stages. I will inject some earlier work also with Federico and Alexander Westphal. Before actually giving you any amount of detail, let me give you a short preview. The issue that we will be dealing with today is that in KKLT, that loci hosting negative d3' charge are often surrounded by a large singularity at minima of the potential in KKLT. So today we're going to deal with this issue for a special case, namely when d7-branes wrap K3. So here's the classical picture where a stack of n d7-branes is surrounded by a rather macroscopic singularity, rendering the entire interior region here singular. And what I'm going to argue today is that when you consider non-perturbative effects, one sees that the n d7-branes actually spread out in their transverse space into 2n more fundamental defects, and each pair you can think of as a d7-brane, which is then a bound state of those two. So that's, and the interior region left behind will be regular but strongly curved. So this is the upshot. Now let me explain to you how that works. And first, let me give you an outline. I'll start, so there are basically three sections. First part, motivation. I'll tell you more about the singularity at the classical level and why it matters. I'll be rather brief on this because Daniel Junghans already gave an excellent talk on this some time ago in this very same series. Then I'll go on to actually explain how the resolution of that singularity works. And then I'll conclude with making a few comments about the instanton expansion in KKLT, using what we've learned before. So let's start with the motivation. The setup is type 2b flux compactifications a la GKP. So we have 4-dimensional Minkowski space and a Calabi-Yau threefold. They are non-trivial F and H fluxes. They are 7-branes and potentially d3-branes. The 10-dimensional metric is not quite of product form. It contains 4-dimensional Minkowski space, or eventually the Sitter space, the internal Ritchie-Flat Calabi-Yau metric, but there also appears the warp factor that depends on the internal directions, and its inverse deforms the internal metric. So this is why it's called a warp product. Then we have a crucial quantity for this talk, the volume modulus, denoted little t, that you can think of as the average of e to the minus 4a, which I'll denote the conformal factor, this piece here. Now, it's well known that the conformal factor e to the minus 4a is sourced by d3' charge. So roughly speaking, after saying the right words, the entire system of 10-dimensional equations of motion collapses to a single electrostatic problem in 6 dimensions. And the source for this that appears in this problem is the d3' charge density. Now we know such problems very well. In particular, solutions have a modulus corresponding to adding the homogeneous solution, i.e. a constant in a compact space. And since little t defined on this previous slide is the average of e to the minus 4a, that corresponds to dialing the volume modulus little t. Now, why do we call it the volume modulus? Because in the limit of very large t, the physical volume of the 6D space approaches t to the 3/2. And that's because the 10-dimensional metric approaches this actual product form everywhere except parametrically close to localized sources. And you see t appearing in front of the 6-dimensional metric that one can normalize to unit volume. So indeed, t measures the volume of the internal space. Now, what are the singularities that we are actually going to consider? Well, wrapped 7-branes are wrapped on 4 cycles, are very well known to carry negative d3' charge. And for the sake of this talk, we're going to assume that they in fact carry all the negative d3' charge that we have in our compactification. So, and we know what it is. The charge is measured by minus chi/24 of the 4 cycle. And this is negative provided tree-level supersymmetry breaking is absent. So if we zoom in close to the location of the wrapped divisor, we find the approximate solution for e to the minus 4a which varies then logarithmically in its transfer space with our radial direction, and the coefficient is positive. Our star here is an integration constant, so we see that at radii that are smaller than our star, this quantity e to the minus 4a becomes negative formally. And that's kind of a problem because if we look at how e to the minus 4a appears in the tangential metric, we see that what actually appears is the square root of that. So we usually think about this thing as a strictly non-negative quantity. However, it's easy to convince yourself that at very large volume, so in the limit t goes to infinity, this radial distance r star, below which the solution becomes singular, scales as follows in 4-cycle volume. And so this is an exponentially small quantity at sufficiently large volume. So you might say, well, if we consider large volumes, then we shouldn't care about this because whatever string theory does to resolve this issue, it's certainly not going to affect KK scale physics. However, note that in the denominator here appears the d3-brane charge, and that can be a large number. So if volumes are only as large as that number, then these effects are still relevant. And indeed they are in KKLT, because for the following reason, KKLT uplift to de Sitter usually comes from a warped anti-d3-brane in a KS throat. So the scalar potential is the sum of two terms. There's a non-perturbative potential that itself has an ADS minimum, and there's the uplift potential, which comes from strongly warped classical physics. So we have these two contributions. Both of them are exponentially small. One, the ADS potential is exponentially small in the KL modulus, the real part of the KL modulus capital T, which scales like little t in the large volume limit. And the anti-brane potential is warped by a factor e to the minus some order 1 number times the 3-brane charge in the throat divided by the curvature radius. The curvature radius at the infrared point. Now, it follows from this that if we ask that the uplift is not supercritical, so we don't run into a decompactification instability, we need to ask that this ratio of charge versus curvature radius to the 4th power is actually somewhat bigger than the value of the Coulomb modulus, which itself scales like 4-cycle volume. Furthermore, for supergravity control, we would like to ask that the denominator, which is the curvature radius, is actually bigger than 1 by some control factor. So we run into the following statement that the physical 4-cycle volume cannot be made parametrically larger than the d3-brane charge hosted in the throat at the position of the KKLT minimum. Now, why is that a problem? Positive d3-brane charge is usually not a problem. However, the positive charge in the throat has to be canceled by a corresponding negative charge on the 7-brane stack. So we have the d3 charge in the throat is less or equal than the absolute value of the d3 charge hosted on the 7-branes. So we find that also the volume of the 4-cycle cannot be made parametrically larger than the d3 charge hosted on the 7-branes. And that's precisely why we lose exponential control over the 7-brane singularity. So this naive factor that I showed you before, which looks like an exponentially small quantity, actually becomes of order 1. And this point has been particularly stressed in this paper by Garber et al. Now, the upshot of this discussion is that in KKLT, the natural scale associated with the d7-brane singularity is actually the KK scale. So it's no longer acceptable to just be ignorant about what's the physics that resolves this. So let me explain to you how does string theory actually resolve the singularity. And we're going to, it turns out that you can explain this rather quickly by making an analogy to F theory. There we have naively a similar problem, namely 1 over gs in the vicinity of a perturbative or 7-plane becomes negative sufficiently close to the source because the profile is 1 over gs, is also a logarithm with positive coefficients, so it naively becomes negative sufficiently close, which of course is inconsistent and looks exactly like the problem we encountered for the conformal factor. Now, of course, the O7 plane is not an inconsistent object. Rather, in F theory, we know that the O7 plane is actually best thought of as a bound state of two mutually non-local PQ7-branes, as famously shown by Sen. So what we want to do today is we want to find the analog of this effect on this side here. In principle, we could pursue something something geometric like F theory. That would be called G theory. But for this talk, we're not going to do this. Instead, we're going to make an analogy to an alternative understanding of this singularity, of this resolution, as explained to us by Banks, Douglas, and Seiberg via gauge dynamics. So here it is. Why does this have to do with gauge dynamics? The string coupling is the U1 coupling on the world volume of a D3-brane probe. So if we use a D3 to probe the O7 back reaction, we realize that the U1 that lives on the D3 is actually the cation U1 in an SU2 Young-Mills theory with 8 supercharges. And furthermore, that the Coulomb branch of this Young-Mills theory is identified with the D3 position in the complex transverse plane of the O7 plane. So all we need to do to quantitatively see how the resolution in the splitting of branes works is we have to look at the Seiberg-Witten solution, specifically at the Coulomb branch, at the singularities along the Coulomb branch. And indeed, semi-classically, one finds a singularity at the origin surrounded by a region of naively negative kinetic terms. And you can think of this as the position of the O7 plane perturbatively. Now, non-perturbatively, we know that that the origin of the Coulomb branch is actually completely smooth, and instead there are two distinct singularities that you can think of as the positions of the two mutually non-local O7 planes, PQ7-branes. So the upshot is that indeed the splitting of the O7 that we know very well from F theory in terms of into two different PQ branes is in one-to-one correspondence with the resolution of the semi-classical singularity of the gauge theory via the Seiberg-Witten solution. And this is what we're going to try to emulate now for RAP-D7 branes. So we want to make an analogy. So let's make this as precise as we can. So we on the one hand, we had an O7 plane and a D3 brane in 10 dimensions, realizing n equals to 2 SU2 theory in 4 dimensions. The relevant gauge coupling is the axodilaton. And indeed, the imaginary part of that becomes naively negative near the center, near the O7 plane, which can be thought of as a duality defect in 10 dimensions. And the duality groups, of course, SL to Z. Now, the splitting of the O7 into two mutually non-local branes, PQ branes, is of course that, so the PQ7 branes are defined by the fact that a string can end on them. So indeed, the BPS dions that we find in the 4-dimensional gauge theory can be thought of as stretched PQ strings. Now, what's the analogous thing that we're going to consider? We're going to consider ND7 branes wrapped on K3, because then we realize also n equals to 2 SUN Young-Mills theory in 4 dimensions. The relevant coupling here, the relevant bulk coupling is tau prime, which is defined like this. And in particular, its imaginary part is the integrated conformal factor, and which varies precisely because the conformal factor varies. There's a further correction by the axodilaton, but that won't be important for us today. Of course, as said before, the problem is that naively the conformal factor turns negative near the position of a perturbative 7-brane. And such a D7 brane wrapped on K3 can again be thought of as a duality defect, now in 6-dimensional 2,0 supergravity. Because that's the supergravity theory that you get by compactifying type 2b on K3. So what's the duality group in that supergravity theory? It's well known, it's 05,21Z, which has as a subgroup an SL to Z that acts in the usual way on this modular parameter tau prime. So we should think of the BPS dions that arise in the 4-dimensional theory as stretched P prime Q prime strings. But I'm putting the primes here because these are not the PQ strings one finds in 10D, but instead the 1,0 string is the F string, the 0,1 string turns out to be the D5 string, so arising from D5 wrapped on K3. So how are we going to use this to address this problem? How are we going to learn how 7-branes split into mutually non-local branes? Well, first of all, the singularities in the field theory should be associated with points in the modular space where mutually local defects coincide, 2 or more of them. So let's start with the singularities in the classical Young-Mills theory. And these are in one-to-one correspondence with coinciding roots of the characteristic polynomial, which are called W, dependent on the adjoint scalar phi, which has n roots ei. Indeed, the W boson mass is given by the differences between, by the pairwise differences between the roots ei. So we can think of these, the roots, as the positions of the ND7-branes in the complex transverse plane. And the W bosons are the stretched F strings, and this is why this mass formula holds here. Of course, in the quantum theory, the singularity structure is very different. Namely, it is well known that instead of the coinciding roots of the characteristic polynomial W, they appear when two or more roots of W squared minus lambda to the power of 2n coincide, where lambda is the strong coupling scale. And this polynomial here factorizes in W plus and W minus, defined like this. Each of them have their n distinct roots, generically distinct, and we get singularities in the theory when two of the roots of W plus or two of the roots of W minus coincide with each other. And of course, in the classical limit, lambda goes to 0, pairs of roots E plus and E minus coincide to give back our root E, the roots EI of the characteristic polynomial, which are the positions of the perturbative D7-branes. So, starting from this, our proposal should be the following. Namely, a D7-brane at position EI should really be thought of as a bound state of two mutually non-local P prime Q prime branes at the positions EI plus and EI minus. Now, how do we characterize these P prime Q prime branes? Well, we look at the dions that arise, for instance, in the SU2 theory. There we have two D7-branes, and it is easy to check that the magnetic monopole has to be the wrapped D5 string. So again, D5 wrapped on K3. And this was already observed by Douglas and Lee a long time ago. And this you can just easily see from just computing the mass of the dion, say in the weak coupling limit, and comparing with the tension of such a string. The 2,-1 dion, stretching from the other pair of defects, can also be thought as a D5 string, but with induced F string charge. Then finally, the F string can be thought of as this. The W boson can be thought of as this junction system. So it arises by stretching an F string collectively between two D7-branes, but they can end only in the D7-branes via this junction system involving the other strings that I talked about before. And using the fact that the D5 string must be able to end on one of the two defects, we can immediately determine what the monotomies are that act on the D7 gauge coupling tau in the usual manner. And they are as follows. We have the perturbative monogamy around the two defects. So those are associated with walking around the wrapped D7-brane, the full one. And but that factorizes into more elementary monogamy transformations associated with walking around either of these two defects individually. With this simple assignment, one of course reproduces the monotomies of the field theory. Now, a point in modular space that will be of particular importance is the origin of the Coulomb branch. And the reason is that classically speaking, this is the point where all the D7s are stacked on top of each other, so they're as close together as they could be. And by looking at just at the characteristic polynomial, one sees immediately that at this point in the quantum theory, the two n defects forming the n perturbative D7-branes actually spread out along a circle of radius of order the strong coupling scale lambda. And this is, of course, the bulk interpretation of the well-known phenomenon in the field theory that the classical R symmetry group U1, which is rotation in the transverse plane, gets broken to Z2n by instantons. And this is exactly what we need to halt the spurious running of the conformal factor, because these defects stop the running via their spreading precisely at the point where naively the conformal factor would turn negative. In the inside region, there's no longer any source, so it stays constant. So this is what the effect we are after. So we say it again, the radial running of the conformal factor is halted by this non-perturbative spreading or splitting of First of all, and this is very simple, as we dial the K3 volume modulus to stronger and stronger coupling, we increase the strong coupling scale, say compared to the Planck scale, and since that measures the radius of spreading here, it makes the scale of this, it increases the scale of the spreading of branes. So in other words, the non-perturbative defects spread out in their transverse plane. So using this, we can arrive at a rather simple effective model, namely that the semi-classical vanishing locus where the conformal factor would naively vanish, it gets replaced by an effective real codimension 1 membrane formed by this array of defects that starts to sweep out the compact Calabi-Yau space. Now in our paper, we show, and I won't have time to go into any detail, that the interior region left behind by the spreading has an order 1 local K3 volume. So curvatures in the interior region are strong, are of order 1, and you cannot dualize them away. Now, as a quick aside, it's not an accident that I drew that I use only 2 colors to draw these defects here in the transverse plane. And the reason is that the defects I've drawn in the same color are actually mutually local with respect to each other, so they can be stacked on top of each other. And by comparison with the field theory, we learn that n mutually local such defects stacked on top of each other actually host certain Argyres-Douglas SCFTs. So now let me make the comments I promised about the instanton expansion in KKLT using what we've learned so far. So what have we learned? That near the KKLT minimum, the non-perturbative spreading of defects becomes macroscopic. So its characteristic size becomes of order the size of the Calabi-Yau. So the strongly curved inside region starts to occupy an order 1 fraction of the Calabi-Yau. So instead of this naive large volume picture where these 7 branes are essentially point-like in their transverse directions, we arrive at this picture here, where their spreading has started to occupy a large fraction of the Calabi-Yau, leaving behind the strongly curved region here, while the other part remains weakly curved. And for later reference, I've also drawn a divisor D that will host the leading ED3 instanton for modular stabilization. Now, since there's a strongly curved region that appears here, we should ask ourselves, can this effect threaten the consistency or the presence of the KKLT vacua, in particular the de Sitter vacua? So let me make some comments about that. And I'm going to argue that I'm going to explain to you why I would find that highly surprising and perhaps even inconceivable. Let me first, the size of the strongly curved region that gets built by driving the Kähler modulus to stronger coupling depends in an exponential way on the Kähler moduli. So the effects that we should see coming from this in the 4-dimensional effective field theory should be those induced by non-perturbative corrections that could be as large as e to the minus 2 pi times the Kähler modulus divided by the charge, plus perhaps perturbative corrections as well. Now we have in 4 dimensions, we have the superpotential and the Kähler potential. So let's talk about the superpotential first. So could there be such a correction? Could it be that the superpotential has its usual constant piece, and then the leading correction is something of this form with a denominator C, where C is of order Q? Is that possible? And the answer is, of course, yes, it is possible, namely if C is the dual Coxeter number of a confining gauge sector on 7 branes. But if that is the case, and C is both C and Q are large numbers, then of course we find that that dynamically at the KKLT minimum, this correction actually scaled down to become of order W0, which is very small. So in this case, we wouldn't actually find a problem to begin with. Now, I don't think this is actually the generic case at all, because it's quite easy to make D3 tuples of order a few hundreds, but getting dual Coxeter numbers of 7-brane gauge theories to that high number is very, very difficult. So instead, what seems to be the generic situation is that the superpotential, as usual, receives starts with the classical term and receives some leading non-perturbative correction with denominator C, and this denominator C is interpreted as the dual Cox-Steiner number of some gauge of some confining gauge, seven-brane gauge theory, and is much smaller than Q. But in that case, there is actually no dangerous correction to the superpotential, because if this is small, this is very much subleading. So, no, sorry, let me go back. So there would be no dangerous correction to the superpotential because, of course, the leading correction is again made small by a small W naught. But now we have to talk about the Kähler potential. And the honest, so if you ask me about the Kähler potential, the honest answer is I don't know. And here I should thank Daniel Junghans for a useful discussion we had. But let me explain to you why I think that might not be a problem. And the upshot is that KKLT ADS vacua are highly robust against corrections to the Kähler potential. And the reason is that if you look at the F terms for instance, the complex structure moduli and the dilaton, of course they have this, they take the usual form, and the Kähler potential multiplies W naught, which is by construction exponentially small. So the F terms in a generic KKLT vacuum are dominated by just the ordinary derivative of the superpotential, so they're highly insensitive to the actual value of the Kähler potential. Now we should consider the F terms of the Kähler moduli themselves as well. And for that, the story is a little bit different because if you turn off the Kähler potential contribution, there's actually no minimum to start with. However, you can write the F term conditions like this, where on the left-hand side, you get the leading instanton or strong gauge dynamics. And on the right-hand side, you get something that multiplies W naught. So if W naught is very small, this should be a very small number. Unless, of course, the corrections to K are fine-tuned in a way that the denominator here scales also as W naught, and that in the small W naught limit. So this is I cannot disprove to you that this occurs, but it looks like a severely fine-tuned situation, and I would be very surprised if that generically happens in KKLT. Then finally, one has to talk about the uplift. And I'm not going to give you the full argument, but one can argue that the picture should be of this form, where at the KKLT minimum, indeed, as said before, an order 1 fraction of the Calabi-Yau has been swept up by the spreading of defects, but the leading divisor that contributes to modular stabilization has to be still at least somewhat in the outside region, because otherwise its action would be of order 1. This then protects the warped throat from severe corrections because the spreading of defects cannot reach the bottom of the throat. So we expect actually no significant modifications to the uplift potential because that's computed from local physics at the bottom of the throat. So let me conclude. First, I've reviewed for you the issue of a large semi-classical singular region in KKLT as introduced in these papers. Then I've explained to you how the singularity gets resolved by a non-perturbative splitting effect of these seven-branes, where a wrapped seven-brane on K3 should actually be thought of as a pair of mutually non-local defects in 60 supergravity. And using this one arrives at a highly consistent picture. One reproduces the singularity structure of the gauge theory, the monodromies of the field theory, and the central charges of the dions that become massless at various points in modular space. And then finally, I've explained to you why we expect that KKLT de Sitter vacua should survive even in the seemingly dangerous regime where an order 1 fraction of the Calabi-Yau has been occupied by this non-perturbative spreading event, leaving behind a strongly curved region. And that's it for today. Thanks for listening. And I think we have time for some questions.
Great. Thank you for the very nice talk, Jakob. Let us all clap for the very nice talk. And let's get to the questions. Let me see. So I think the first one is from Daniel. Daniel? Oh, there we go.
Yeah, hi. Yeah, very nice talk. Thanks a lot. I just wanted to make a comment about the last part of your talk. So as you know, I see it a bit differently than you. So I think in this highly stringy regime, the Kähler potential should be expected to get large corrections, both from curvature corrections and also large warping corrections. So I wouldn't really know how to argue why the KKLT potential should stay the same way. And I think it's quite speculative to assume that the Sitter vacua will survive and that the potential will stay the same or almost the same as it is in the supergravity regime. So I think one would have to prove that somehow. At least from my point of view, I cannot see why you would expect this to stay the same.
Yes, I mean, I'm not claiming that I've proven this, and I agree that this should be checked. So the only thing I've said is that I've stated what would be necessary in terms of how the Kähler potential would have to behave such that the Sitter vacua would, or that the KKLT vacua would disappear. So it's possible, but and one should check this. That's true. But I think it looks like something that's very fine-tuned. So one can debate about the likelihood of that happening.
Okay, thanks.
Thanks for the question.
Ander?
Okay, can you hear me?
Yes.
Yeah, hi.
Okay,
Yeah.
right. Hi. Thank you for the nice talk, Jakob. So if I'm understanding well, the origin of the whole thing comes from taking the GKP ansatz, and then you find this electrostatic problem, right? I mean, there was this equation by the very beginning of your slides. So what would happen if you relax the GKP ansatz? I mean, say you allow for, I don't know, just a Kähler manifold instead of some conformal Calabi-Yau. What would happen in this case?
I mean, that's of course more complicated. I don't know. I would expect that at least qualitatively, it's still true that the warp factor is sourced by the three-band charge in this way, and that you get, so I mean, the reason why you get strong warping from positive D3-band charge is that you cram together D3 charge, and then you need some effect that stretches this to larger volume. So I think this is generic. This should happen all the time, but you can probably not phrase it quantitatively quite like this.
Okay, so you didn't explore this option, right? I mean,
no, we didn't. No.
Okay.
I don't expect qualitative changes, but quantitative ones, of course, yes.
Right. Thanks.
Thanks.
And Lisa?
Hi, so first of all, thank you for a really, really good talk. Really enjoyed it. I just have a question though. From what you're doing with that, would I conclude that I wouldn't be able to use fundamental D3 branes? I mean, it seemed to rely very heavily on the fact that you're using wrapped D7 branes. And is that just a logistical thing that you can only know how to decompose them in that case, or would this just not work with fundamental branes?
Yeah. One can, so the problem that occurs is a general one for negative D3 brane charge. So whenever you cram together negative D3 brane charge, you immediately get this large singularity. And this can come from various sources. That can come from wrapped seven-branes, intersecting seven-branes, O3 planes. I don't expect that the situation will dramatically change when you do that, but it's harder to study. So the only reason why we focused on D7 branes wrapped on K3 is that we can use the Seiberg-Witten solution. So we have 8 supercharges instead of 4, and that makes life easier for us. One can probably make a similar argument for 3 planes. It's a bit more mysterious in a sense for D7 branes wrapped on devices with many normal bundle deformations, because then the gauge theory is IR free, and it's kind of strange, and it's kind of hard to see how, at least from the gauge theory perspective, how the resolution should happen precisely, because you can't use gauge instantons.
So what would be the analog of the dions, or that the D7 are made up of?
Well, I think it will remain true for general seven-brane theories that you can think of the magnetic monopole as a wrapped D5. I think that's universal, and of course the W boson is a stretch F string. I think this remains the same.
Okay, thanks.
Okay, and finally, Arthur?
Yes. Hi. So, Jakob, could you go back to the slide where you showed why KKLT should after all work, where the Kähler potential slide?
Yes.
just to see that I understand correctly. Yeah, that one. So my worry would be that on the very last line, you know, that somehow kt, or the first derivative of k with respect to t is something of the type 1 over volume. And you see, if the volume goes to 0, of course, that would be a problem. Now you see the volume in your case doesn't go to 0, it takes order 1 values. Yeah. But still, I mean, I naively expect a singularity for sufficiently small t if I'm naive. And that's what my concern is. I'm simply, my interpretation of what happens here is that in this particular constructions KKLT require, the volume somehow becomes small in the sense of the expansion breaking down earlier than you think. At the values of t where you want to stabilize, that thing explodes. And so I think there is a good reason to be afraid of a singularity in dtk. Okay, I think the world will be very beautiful and very possibly it works as you describe, but there is a danger of a singularity here.
Yeah. So what makes me hopeful that this does not happen is that we were able to explain the resolution of the singularity, at least at its immediate volumes, just using the degrees of freedom that we already had in the four-dimensional EFT. So I'd expect a new singularity to come in whenever there are new mass states becoming new states becoming light. And if I look at this setting where the seven-brane, where the defects spread out in the transverse space, they generically shouldn't hit other defects because that happens at real codimension 2. So I would be very surprised if there's actually a singularity that occurs until the very last stages when the entire manifold has been swept up.
Okay.
It could be, and I think at the technical level, what the thing you're afraid of is that what if the Keller corrections are such that the point in field space where KKLT would live isn't even there anymore?
Precisely. It's beyond the point where you can go. I mean, the modular space.
Yeah, so the modular space metric changes completely, and this point is completely removed. It's a possibility. It's just I would find that a bit surprising because when W0 is small, the superpotential doesn't receive any large corrections while that happens. So it seems a bit it would seem a bit strange to me.
Okay. I have another question concerning your actual calculation with the K3. I mean, it seemed to me that it was crucial that you have some kind of modular space in the sense of moving branes that are wrapped on the K3 transversely to each other.
Yeah.
Now that, of course, will in general not be the case. If you take a proper Coulomb, I mean, it will not generally be, say, K3 times a plane.
Yes.
And so I wonder how you would imagine extending your argument in that case.
Yeah. I mean, at this stage, it's very much by analogy. We have a case where we can see this directly, so I expect something like that to happen also for in the general case. But it's not. Yeah, I mean, you're right. I mean, it's in part also what Lisa asked, right? What if I take seven-branes wrapped on surfaces that have many moduli? Then it's not clear what happens because it could still be that there's something very similar happening, but it's not clear how to see that from the gauge theory. There's no modular space where I can just transversely move them apart because the first generalized is non-trivial. So they always intersect. So it's hard to use the gauge theory to actually get the insight in the bulk.
I see.
But it could still be the same. I mean, I would think that, but it's not a proof.
Thank you.
Thanks.
Great. So with that, it looks like there are no more questions. Let's thank both our speakers once again, Andrew and Jakob.